Okay, so I want to go over now the compare Bohr's model with the modern model of the atom. So what I want to through first were some problems that we had with Bohr's model. One of the problems is that Bohr's calculations only worked for hydrogen, as I said. Remember, it could only work for atoms with one electron. It couldn't be used to explain spectra of more complex atoms. So what happened then was quantum mechanics was developed to describe the location of electrons in a region of space for more complicated atoms and also for hydrogen. So what Bohr said later on was that if you're not shocked by quantum mechanics, then you're not really understanding it. So what I'm telling you here is that Bohr was a brilliant man. He won the Nobel Prize. He was a very great scientist, but he found quantum mechanics complicated. I would say nearly anyone that encounters quantum mechanics finds it complicated. So there's going to be parts of this you're not going to completely understand, but I want you to have a basic knowledge of quantum mechanics. So what we talk about now is we talk about an electron cloud. And I want to show you in this map here. Here we have the nucleus. Here we have an electron, which is just kind of moving around. If we look at this map here, all these dots represent where the electron has been at some point in time. So this is showing you the probability of where the electron might be in the future. Areas where there are more dots on this map give you an indication there's a greater likelihood that the electron will be in there in the future. Areas where there are very few dots on this map are areas where the electron has not been very often in the past and will not likely be in the future. So if you think about out here, the electron has never been there in the past, so we don't expect the electron to ever be there in the future. Close to the nucleus is where the electron has been very frequently in the past, and we'd expect it to be there in the future. So these dots do not represent the electron path. They also do not represent lots and lots of electrons. They're just showing you the likelihood of where the electron might be in the future. So somebody named Schrodinger came up with a wave equation. So what he did was he came up with math equations that describe the probability or the likelihood of where the electron might be at a certain period of time. There are many versions of the wave equation. So I do not expect you to know this wave equation. I'm just showing you what one looks like. One thing I do want to point out here is that in math class, if you're taking algebra, I mean, not algebra, but in calculus, you will be working with functions of different variables. Here we have an equation that's a function of actually 4 variables. In algebra, you usually have your y is dependent on your x. Here we have a value that's dependent on 4 variables that we plug into the equation. These are very complicated calculations. So we're going to be going over what each of these 4 variables represents and how those relate to where the electron is in an atom. So what we talk about with the quantum mechanics is we talk about the probability. The probability of finding an electron in a certain region in the atom is described by an orbital. An atomic orbital is a region around the nucleus where an electron is likely to be found. The shape of this orbital is described by the equation I just showed you, a Schrodinger wave equation. So the 4 variables are kind of like parts of an address for the atom. Just like when you look at your address, you have your street number, you have your street name, you have your city, you have your state, and if you were sending it abroad, you would also have the country. So also, if you think about if you go to a rock concert or to a football game, if you look at your ticket, you will have a level, you will have a section, you will have a row number, and you will have a seat. So you actually have about 4 different things that are described on your ticket, and nobody else's ticket will have exactly the same 4 pieces of information. There will be something different. Otherwise, you would get to your seat and you would find that somebody else has exactly the same seat. That can't happen. So the first part of the address for an electron is called the principal quantum number, and this is symbolized as N. This is the energy level, and it will describe how large the orbital is. So here we have N with 3 different values, 1, 2, and 3. If you notice, when we have 3s, the orbital is much larger than when we have 1s. You notice here in this case, the shape is the same, but the size is very different. We can imagine the nucleus is in the center of each of these. So electron in 3s is further from the nucleus than the electron in 1s. So the principal quantum number corresponds to the energy levels in Bohr's model of the atom. So if you remember Bohr's model of the atom had rings, we had different energy levels. We're seeing the same thing here. They both describe how far from the nucleus the electron is. Just that quantum mechanics gets to be much more complicated than Bohr's model. So what we see is the higher the N is, the number that corresponds to N, the further away the nucleus is from the electron. And what we see is that the electron itself has more energy. So N is equal to 1, the electron's very close to the nucleus. N is equal to 2, it's further away. N is equal to 3, it's still further away. 4 and 5. So it just gets larger with each energy level. Now, if we look at our periodic table, the energy levels actually correspond to the row numbers of our periodic table. We call these periods. So we actually have 7 periods or 7 rows on our periodic table, and there are actually 7 possible energy levels in our atom. So the elements that are on the very bottom of our periodic table have actually 7 energy levels. Hydrogen and helium in the first period of our periodic table only have 1 energy level. Okay, so electrons exist in energy levels according to their energy. So we have 7 principal energy levels, and these correspond to the rows on a periodic table. But we also have sublevels. So these actually describe the shape of our orbitals. So we're going to go over what sublevels are. So electrons exist in orbitals. The orbitals are found in each sublevel, which determines the orbital shape. And the sublevels combine to make up of our principal energy levels. And the sublevels actually make up our electron cloud that we imagine. So we're going to be going over L, which describes the shape of our orbitals. So L is dependent on N, so I'm going to go over what exactly that means. There's 4 different values of L. So 4 different orbital shapes. We have L is equal to 0, L is equal to 1, which looks like a dumbbell. L is equal to 2, where you have double dumbbell. And L is equal to 3, which looks kind of like a flower. And these are given different letters. When L is equal to 0, that's S. L is equal to 1, that's P. L is equal to 2, that's D. And L is equal to 3, that's F. And we'll go over each of those separately shortly. So One thing I do want to show you here is how the L value depends on N. So when N is equal to 1, L can only equal to 0. When N is equal to 2, L is going to equal to 2 minus 1, which is 1, and it's going to equal to 0. When N is equal to 3, L is going to equal to 0. It'll equal to 2, and excuse me, 1, 2, so actually 0, 1, and 2. And when N is equal to 4, L is going to equal to 0, 1, 2, and 3. So L is going to equal to 0 all the way up to N minus 1. Okay, so what this tells us that the first energy level will just have one type of orbital. The second energy level will have two different types of orbitals. The third energy level will have 3 types of orbitals, and the fourth energy level will have 4 different types of orbitals. Okay, so the first energy level only has one sublevel, that's going to be S. The second energy level is going to have 2, that's S and P. The third is going to have 3, S, P, and D. And the fourth energy level is going to have 4, which is S, P, D, and F. So what we see is the larger the energy level number, the greater the volume of space around the nucleus, and the more sublevels we will have in that particular energy level, which will mean more orbitals and more electrons. So energy levels that are higher will be holding more electrons than energy levels that are lower. Another quantum number is the magnetic quantum number. The magnetic quantum number is dependent on L. So L is dependent on N, M sub L is dependent on L. So M sub L will have values anywhere from negative L to positive L. So I'll go over that. This tells you how the orbital is oriented in space. So it tells you the exact orbital within a sublevel. So we'll be going over this shortly, so don't draw those pictures, but I want to show you how M sub L relates to L. Okay, so when L is equal to 0, M sub L will only equal 0. When L is equal to 1, M sub L will equal to negative 1, 0, and 1. When L is equal to 2, M sub L will equal to negative 2, negative 1, 0, 1, and 2. When L is equal to 3, M sub L will equal to negative 3, negative 2, negative 1, 0, 1, 2, and 3. Okay, so you're going to see how this comes into play with the next slide. So when we have the S sublevel, remember that's going to be a spherical shape. That might be a way to remember the S is the sphere. L is equal to 0. There's only one value for M sub L, as we mentioned on the last slide. So there's only going to be one possible S orbital. So each S sublevel will only have one orbital in that sublevel, which will be that sphere. When we have L is equal to 1, as we said on the previous slide, M sub L could have 3 possible values, negative 1, 0, and positive 1. So there's actually 3 possible p orbitals. There's going to be 3 of these, They're going to be oriented in different directions in space. Each of these are shaped like a dumbbell. So on the next slide, I'm going to show you this 3 different p orbitals. Here we have px. It's oriented along the x-axis. Py, which is oriented along the y-axis, and Pz, which is oriented along the z-axis. If your element has all 3 types of orbitals, px, py, and pz, they will overlap and all of them will be centered around the nucleus. So this last picture is showing you just how they all overlap and center around the nucleus. And they'll be 90 degrees apart from each other. With the D sublevel, remember L will equal 2 in the D sublevel. So there's actually 5 different values for M sub L. It'll be -2, -1, 0, 1, and 2. So there's actually 5 different ways the D orbital will be oriented in space. These are shaped like a double dumbbell. There's also one that looks completely different, shaped like a dumbbell with a donut. So in the next slide, I'm going to show you these 5 different d orbitals. So these are oriented along the different planes in 3-dimensional space. And then the last one, dz, this dz squared, is the dumbbell with the donut. Just know in general that there's 5 of these, and they're generally shaped like a double dumbbell. The last one is the F sublevel. Here, L is equal to 3. Now remember, there's 7 different values for M sub L. So there's actually 7 different ways the F orbital will be oriented in space. Now, I don't expect you to be able to draw these or remember the exact shapes, but just know that in general, they're shaped like a flower. So just know they're shaped like a flower. Okay, so we're going to go over one more thing, and then I'm going to show you guys we're going to review this information with a sheet that I have on Google Classroom. So these orbitals are all centered on the nucleus. They will kind of overlap each other, and they create that kind of that random cloud shape we see, but that's made up of all the atomic orbitals. Okay, so before we go over the device, or the sheet on Google Classroom to review all this information, I want to go over one more quantum number, which is M sub s. So there's a spin quantum number. This describes the spin of the electron. The spin is either positive a half or negative a half. So the electrons can spin in opposite directions. We have 2 electrons per orbital, one spinning kind of in a clockwise direction, the other one spinning a counterclockwise direction. So this just tells us that each of those orbitals, like each p orbital, can only hold 2 electrons. The electrons then are spinning in opposite directions. Okay, so now I'm going to pull up the sheet that's on Google Classroom, and we're going to just review this information we went over so far. Okay, so now to summarize the information that we went over about the different quantum numbers, about the energy levels, and so on, I want you guys to do this worksheet along with me. This is in Google Classroom. So you guys can print this out or pull this up, and we're going to work through this together. So remember, the first quantum number we went over is the energy level number, and that's symbolized by N. And remember, the values for L, or the number of sublevels, are dependent on N. So when N is equal to 1, there's only one possible value for L. So there's actually only one sublevel in energy level 1. The name of this is S. It's a spherical shape, so just draw a circle here. Remember, the S sublevel only has one type of orbital, so there's only one. We can only put 2 electrons in an orbital, So that would be 2. And there's only one orbital in the first energy level, so that's going to be 1 with 2 electrons. With the second energy level, since n is equal to 2, there's 3 possible values for 2 possible values for L. So there's going to be 2 sublevels. So there's going to be S and P. So we're going to have a sphere and we're going to have a dumbbell. There's 1 possible S orbital and there's 3 possible P orbitals in the P sublevel. This S sublevel will hold 2 electrons. The P sublevel will hold 6. There's 4 orbitals in the second energy level holding 8 electrons. If we go to the third energy level, since n is equal to 3, there's 3 possible values for L. So we have S, P, and D. So we have a sphere, a dumbbell, and a double dumbbell. So we have 1, 3, and 5. Notice we go up by 2 each time. And we have 2, 6, and 10. There's 9 orbitals in the third energy level holding 18 electrons. In the next energy level, since n is equal to 4, we have 4 possible values for L this time. So we have S, P, D, and F. So we have a sphere, a dumbbell, a double dumbbell, and a flower. This one has 1 orbital, 3, 5, and 7. Notice we're still going up by 2 each time. We have 2 electrons with this one, 6, 10, and 14. The number of orbitals add up to 16. The number of electrons add up to 32. Okay, so I want you guys to understand what the different quantum numbers stand for, what they mean. I want you to also understand that the shapes of the orbitals that we see has been predicted by using Schrodinger's wave equation. And then next, we're going to start going over electron configurations. And once you know your electron configurations, which are actually pretty easy, it's going to be pretty easy for you guys to actually figure out the number of orbitals, the number of electrons, and so on for a particular energy level. Okay, so good luck on the next step, and make sure you're watching the next screencast.